Well, everybody, welcome to week 10 of the quarter. I know week 10 is definitely on the stressful side for a lot of us. So, thankfully, if it's any consolation, the lectures this week are going to be definitely on the shorter side. Um, I haven't quite figured out yet if this lecture is going to be, like one quote longer lecture without a second part, or if it's going to be two shorter parts. But I suppose, um, given that when you're watching this, I will have already made that decision, you already know what I went with. If you remember last week, we sort of ended the week by talking about this concept of the algebra of matrices, right? We looked at how they add, how they subtract, and how they multiply. Today we're going to look at to what extent they divide. Okay, like how can you create this concept of division of matrices? And we're going to go about that in sort of a different way. Okay, and that's through studying an idea called inverse, Inverse, matrices. And the motivation behind this is if you remember, when we're talking about real number multiplication, um, or rather, when we talk about real number division, right, um, you can formulate real number division as multiplication by an inverse. And there's sort of two really important properties that happen with this multiplication by an inverse. And that's when you multiply an object times its inverse, right? 2 times 1/2, you get 1, okay? And the second is this concept of 1, right? And the really important thing about 1, right, is if you take 1 and you multiply it by a number, it's equal to taking that number and multiplying by 1, right? Because multiplication in the real numbers commutes. But most important is that multiplying by 1 doesn't change your real number. We seek to see if there's a similar concept among matrices, okay? Something like an identity matrix, right? It has to be able to do this for any matrix A, or at least any matrix where it's defined. And if you think about defining matrix multiplication on something like this, you'll kind of realize pretty quickly that both 1, whatever our 1 is, and A, our matrix, all have to be square, okay? We're going to pretty much, I believe, for the majority of this week, only consider square matrices because the way that they multiply is just a lot nicer. And these sort of structures can't be defined for matrices of arbitrary size like that. And here's how you form an identity matrix, okay? They're called I, and then there's usually a little subscript that tells you the dimension of the matrix, right? So I2 is a 2 by 2 matrix that functions as the identity, and it looks like this. 1's along one diagonal, 0's along the other, okay? Right, where, this is the diagonal of the matrix. When you hear someone, if you hear me or another person reference the diagonal of a matrix, that's always this guy. If we had a look at, say, I3, it's going to look pretty similar, right? 0, 0, 1. So the identity matrix has 1 along the main diagonal and 0 everywhere else, right? If we were looking at, some arbitrary n by n matrix, you'd have 1, 0, 0, and so on. You'd have 0, 1, 0, and so on, and so forth. I think you get the gist, and then a 1 in that corner, right? And it's worth sort of thinking through like that this would work and sort of how it would work. And I'll give you one example right here. Actually, I'll give you two. the first one is actually going to be a little interesting because these identity matrices still function as an identity matrix with rectangular matrices, right? So if I multiply I2 by 3, 5, 6, negative 1, 2, 7, right? What are we going to get there, right? Well, this is a 2 by 2 by a 2 by 3. So we should get a 2 by 3 out the other side, right? Well, what's this entry? Well, this entry is going to be 1 times 3 plus 0 times negative 1. So it's going to be 3. This one is 1 times 5 plus 0 times 2. And if you notice, here we have 1 times 6 plus 0 times 7. What this identity matrix does is this 1 gives us the entry we're looking for, right? If we're going here, we have 0 times 3 plus 1 times negative 1 for negative 1. And so it takes it and it gives us the exact same matrix back, right? If you were to do the same thing for, say, a 3 by 3 matrix, right? Maybe we have negative 1 times 7 times 1/2. Not times, these are just entries in a matrix. Negative 2, 0, 7, right? And we multiply that by, say, I3, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Well, when we carry out this multiplication, it's the same idea. What goes in this entry? Well, it's 1 times negative 1, 0 times 7, and 0 times 1/2. So negative 1, right? For the same reason, right, this entry is going to be the inner product of this row and this column, right? So it's going to be negative 1 times 0, 7 times 1, and 1/2 times 0 for 7, right? And if you see for each of these 9 elements, right, we're going to have this 1 select the one we want, and then the zeros are going to take away the other 2. And we do indeed have this function as our identity, right? It doesn't change the matrix that we multiply it by, just like how when you multiplied a real number by our identity, it didn't change the output, okay? So now that we have an identity, right, we have a 1, okay? What can we say about this idea of an inverse, okay? So let's say, right, A and B are square matrices. This is where we restrict to squares, okay? And let's say A times B is equal to B times A. Okay, so this right here says that we have to have square, right? When both of these are defined. And if that equals the identity, right? So because it's equaling the identity, we need to say that, these are square n by n matrices, right? We can say then, we say B is the inverse. That's our fancy word here, is the inverse of A. And we write B equals A inverse, right? And so that gives us the property that we would expect, right? Now it looks like the real numbers, right? A inverse is equal to A inverse A is equal to the identity, right? What's important to note here is that what this isn't saying, this is not like 1 over A, right? That's not defined in any meaningful way. What A inverse is it's the matrix such that this is true, okay? And we'll sort of spend the rest of our lecture looking at how to find and calculate these. Okay, so let's start with the 2 by 2 case. Okay, because that tends to be a little bit easier. Okay, so let's say A is 2, 1, 5, 3. We'll say B is 3, negative 1, minus 5, and 2. Okay, and we want to verify B equals A inverse, right? So this is the claim, and we want to verify that it's true. And to do this, we have to do 2 separate multiplications, right? We need to verify both. It is not enough to only verify one, okay? You can absolutely run into some really nasty matrices where AB equals I, but BA does not, right? Because our matrices don't commute. So let's look at this, right? A is 2, 1, 5, 3. B is 3, negative 1, negative 5, 2. Right? So what happens when we multiply these? Well, in this entry right here, we're going to have 2 times 3, which is 6. Looks like minus 5, so that's a 1. It's a good start. Right here, it looks like we have negative 2 plus 2 for 0. Right here, it looks like we have 5 times 3 for 15, minus 15 for 0. And then right here, looks like we have 5 times negative 1 for negative 5, plus 6 for 1. Okay, so that's good, right? Let's look at BA. Okay, I'm going to paste that guy right here and rearrange our system like that and see what happens. Okay, so what do we get here? Well, we have, it looks like 2 times 3 plus 1 times negative 5, so once indeed 1, or once again, indeed, we have 1. Right here, it looks like we have 3 times 1 minus 1 times 3 for 0. Right here, we're going to have minus 5 times 2 for 10. We end up with 10 minus 10 right there for 0. And then for the final one, looks like once again negative 5 minus 6 for 1. Okay, so indeed, we have that B inverse does equal A. Okay, so now the question is, how do we calculate these, right? How do we find the inverse of a 2 by 2 matrix? Okay, and let me show you how. Okay, so let's say A equals this matrix right here, right? A, B, C, D. Okay. Then we have the following. We have A inverse is equal to 1 divided by, okay, this is a scalar that we're multiplying by, 1 over AD minus CB, okay, where, you know, these guys are these entries. And then that is multiplied into the matrix D minus B minus C A, okay? So what you're doing is you're switching your diagonal elements and you're negating the off-diagonal elements, okay? We also say that if AD minus CB equals 0, well, then A does not have an inverse. That is one of the interesting things that we get in the world of matrices, right? In the real numbers, everything has an inverse except for 0, right? But in matrix land, you can absolutely have these matrices that don't have inverses, so you can't always divide, okay? So let's do an example of this, okay? Let's say A is equal to, we'll go 4, 5, 2, 3, okay? We'll say find and verify A inverse, okay? And so let's take a look at this. Using our formula from above, okay, we're going to have 1 over AD is this product here. That's going to be 12. And it's going to be minus this product here, right? AD minus CB. So 12 minus 10. And then we're going to switch the diagonal elements. So it looks like it's going to be 3 and 4. And we're going to negate the other two, okay? And, well, what does this come out to? This comes out to 1/2, right? 10 minus 12 is 2, times 3 minus 5, negative 2 and 4. Or if you want to distribute that in, looks like it's going to be 3/2 minus 5/2, negative 1 and 2, okay? It's worth noting this product right here, AD minus CB, that's the thing that we call the determinant of this matrix here, this original matrix. And it turns out that if your matrix has a determinant of 0, well then the matrix doesn't have an inverse because in this case we can't divide by 0. The lecture on Thursday will be all about this concept of a determinant, but I just wanted to expose you to that is why we're doing this. That's where this AD minus CB comes from, and we will explore that more on Thursday. Okay, so now we have A inverse. Okay, and we want to take a look at A times A inverse, right? Because we want to verify that the thing we found is actually what we're claiming it to be. So we have 4, 2, 5, 3 times 3/2 minus 5/2 minus 1 and 2. Okay. And what do we get when we perform this matrix multiplication? Well, we're going to have 4 times 3/2, which looks like that's going to be 6. Looks like that's minus 5. For this entry, it's going to be 4 times minus 5/2, or minus 10, plus 5 times 2 for 10. For this entry, we're going to have 2 times 3/2 minus 3, so that's going to be 3 minus 3. And for this entry here, it looks like we're going to have 2 times minus 5/2 for minus 5, plus 3 times 2 for 6. So once again, 6 minus 5. And when you carry out that arithmetic, you get 1, 0, 0, 1. Okay, so that's the identity. We still need to calculate A inverse A, and I'm going to have y'all do that at home, verify that that matrix multiplication does indeed do what we claim, okay? So now we have the tricky situation of trying to find the inverse of an n by n matrix. And unfortunately, I can't prove to you why what I'm about to show you works. But it does, and if you continue on in your math journey, eventually you will be able to show it, okay? And so here's what we're going to do. We're going to take some n by n matrix A, okay? So we have A, and we'll call this guy n by n, okay? And we're going to form a big old augmented matrix, okay, on this matrix right here, okay? So A11, A12, all the way to A1n, okay? A21, A22, all the way to A2n, and I guess I'll fill in all of these, right? AN2, and then this guy's ANN. So we're going to augment that, okay, with the identity, okay? So we're going to form a matrix that's n by 2n, okay? Over here, we're going to put the identity matrix, okay? Ones along the diagonal, zeros everywhere else. So if you want to think about these as blocks, right, this is equal to, you know, the matrix A, and then we're augmenting that with the identity, okay? And then here's what we're going to do. We're going to use the elementary row operations that we looked at over the past couple weeks on this matrix, okay? And if we do that step by step, this guy is going to get transformed, right? When we take this guy all the way to RREF, okay, that's like we looked at like RREF last week because it was kind of cool and handy and like lets you, you know, avoid back substitution. But if you put this in RREF, what you get is an identity matrix, right? You're going to have ones along the diagonal and zeros everywhere else. And the really cool thing is if you do RREF, or I guess Gauss-Jordan elimination, to put this guy in RREF, you get the identity matrix on this side, and the other side, through that process, is transformed into the inverse matrix, okay? Like I said, unfortunately, we can't go about proving this, so we'll just have to do a couple of examples to show that it works, okay? So let's start with that, okay? So let's say A, let's set him equal to 1, -2, -4, 2, -3, -6, and we'll say -3, 6, 15, okay? And we want to, just as before, find and verify our A inverse, okay? And so, well, what did that ask us to do, right? We want to form the augmented matrix, starting with A, right? Make that a little bit nicer. And then we want to augment that with the identity. 1, 1, 0. That should be a 1. And then zeros everywhere else, okay? And we're going to step by step put this into RREF, and then our other guy will magically become our identity, or will become our inverse, okay? So if we're looking to put this guy into RREF, we have this nice 1 up in the corner, and so we want to use that to take away these, okay? So I'm saying that we should do, it looks like row 2 minus 2 times row 1 to affect row 2, okay? So what we can do is we can copy down this guy. We're changing row 2, so that guy's got to get deleted, okay? And so what's going to happen here? Well, we're going to have 2 minus 2 for 0. Looks like we're going to have 3 plus 4 for 1. Looks like we're going to have -6 plus 8 for 2, okay? I'm guessing we're going to have 0 minus 2 for 2, 1 minus 0 is 1, and then these are both 0, so nothing changes, okay? So that's our first step, right? Second step, we want to get rid of this -3. Once again, we can use row 1 to accomplish that, right? So we're going to take row 3, so we're going to add to it 3 times row 1, redefine row 3, okay? So since we're redefining row 3, the other rows will stay the same, okay? And what are we going to get? Well, it looks like we're going to have 3 plus 3 for 0. We're going to have 6 minus 2 times 3 for 6, so 0. So thankfully, we got this 0 too. That doesn't always happen, but it's nice when it does. And then for this last one, we're going to have, it looks like 15 minus 12 for 3, okay? And then what happens on the second side, right? We have 1 plus 3 for 3, have 0 and 0 for 0, and 1 and 0 for 1, okay? So what do we want to do next, right? We've cleared these zeros. It would seem to me like the next logical thing to do would be to get column 2 like the way that we want it, right? Because when we're in RREF, all of the entries above and below our leading entry need to be 0. This one's 0, that one's a -2. That's not great, right? So how can we fix that, right? We want to redefine row 1, and we can add to it 2 times row 2, right? Because then 1 times 2 is 2, those will cancel, and use that to redefine row 1, okay? And the reason that we want to use row 2 here is because of this nice 0, right? Because we have this 0 here, we're not going to mess up the 1, right? Think about if we were trying to clear this 0 too, right? If this said, 5 for some reason. We could multiply equation 1 by something to clear the 5, but it would take away this 0, and we want to keep this 0. So that's why we use, this 1 to clear this -2, and whatever entry is there, okay? So we're redefining row 1, so we're going to need to erase row 1, okay? And what happens to it? Well, like we said, we have 1 plus 0 keeps our 1, which is great. That's exactly what we wanted, okay? We're going to have -2 plus 2 for, what would you look at that? 0, the other thing we wanted, right? We're going to have -4, looks like plus 4 for 0. That's nice. Once again, that's sort of like how we got this 0. Doesn't always happen, but it's nice when it does, okay? For this entry right here, we would normally have 1 plus 2 for 4, except I did notice that up here, we did 0 minus 2, so this 2 should be negative. So that 2 should be negative, so then we have 1 minus 4 for -3, okay? And then in the second column, it looks like we have 0 plus 2 for 2, and then 0 and 0 gives 0, okay? So what do we want to do next? Well, now we're interested in clearing this of zeros. And there's a number of ways to do that, but the other thing that we really want is we want this to be a 1, right? Because the first non-zero entry of each row needs to be a 1. And so this 3 needs to become a 1. And the easiest way to do that is simply to multiply row 3 by 1/3, right? And so what that's going to do, it's again copying this guy, is it's going to take each of these entries and it's going to divide them by 3, right? So 3 becomes 1, our 3 becomes 1, and our 1 becomes 1/3. Unfortunately, when we start working with these inverse matrices, fractions become even more common, and we just kind of got to be careful when we're working with them, okay? So what happens next? Well, now that we have a 1 here, we want to clear this 2, right? Clearing this 2 is the last thing that we need to do to put this guy into RREF. And so let's try and do that, right? We can take row 2, and we can subtract from it 2 times row 3, right? And then use that to redefine row 2, right? So what's going to happen there? Once again, copying this guy. Suppose I didn't need to draw that. So we're redefining row 2, so row 2 gets erased. We have 0 and 0 is 0. We have 1 minus 0 is 1, right? So the things that we didn't want to change didn't, which is great. Looks like we're going to have 2 minus 2 for 0, exactly what we wanted. Forgot to carry through my negatives here. So that should be a -2, and that should be a -2. So we're going to have 2 minus 2, or -2 minus 2 for -4, okay? And then we're going to have, it looks like 1 minus 0 for 1. And then we're going to have 0 minus 2/3 for -2/3, okay? And now we have the identity matrix here, and through the magic of these row operations, I claim that that's our identity, okay? But let's verify this, right? We'll need to go into the next page for it. But if we're going to do, say, A times A inverse, well, our A was 1, -2, -4, 2, -3, -6, and -3, 6, 15. And the A inverse that we calculated was -3, 2, 0, -4, 1, -2/3, and 1, 0, 1/3, okay? And we want to carry out this multiplication, okay? Remember, that's taking the inner product of this row and this column for this entry, right? You have to go one at a time. So when we take these inner products, looks like we're going to have -3 plus 8 for a total of 5, minus 4 for a 1, right? For this entry here, we're going to take the inner product of this row and this column. So it looks like we're going to have 2 minus 2 plus 0 for 0. For this guy, we're going to take the inner product of this row and this column. So we're going to have 0. It looks like we're going to have plus 4/3 there. We're going to have minus 4/3 there. Comes out to 0. Okay. Moving on to our next row. Inner product of this row and this column. Looks like we're going to have -6 plus 12 for a total of +6, and then -6 again for 0. For this entry here, we're going to take the inner product of this and this, so it's going to be, so it looks like 4 minus 3 plus 0 for 1. And then for the last entry here, we're going to have the inner product of these two. Looks like we're going to have 0 there, a +2 there, and then a -2 there for 0. And then for our last row, the inner product of these two, this one's going to be a little bit bigger. It looks to me like we're going to have +9, minus 24, and 15, which indeed does come out to 0. Next, we're going to have 3 and 2 for 6, minus 6 for 0. And then finally, inner product of these two, -3 and 0 give us 0, so we don't need to worry about that one. Here we're going to have -4. Here we have +5. Add those together and you do indeed get 1. Okay. Just as before, I'm going to have you calculate A inverse A at home. Go ahead and it is really good practice to go through this matrix multiplication. It's a little bit wild and wonky, and we're not necessarily always used to it, okay? Let's give one more example of finding this matrix, and then we'll move on to our last topic, okay? So when we do this, this is what we're going to look for, okay? We're going to find the inverse of, let's say, 2, -3, -7, 1, 2, 7, and 1, 1, 4, okay? And the way that we do this is we take our matrix, we take it, and we augment it with the identity, so 1, 1, 1, and a bunch of zeros. And I know that we're only doing this with examples of 3 by 3s, but this process works in general, right? You could put any size matrix, follow this along, and it would work, okay? So with what we're doing with this guy, remember the thing that worked really nice about our last one was we had a 1 in the upper right-hand corner. In this one, we don't, but if you remember, one of our elementary row operations that we can do is switching the order of rows, right? So I can take this guy and I can take row 1 and I can switch it with row 2, and we're going to get the following matrix after we do that, right? We're going to get 1, 2, 7, 2, -3, -7, and 1, 1, 4. But here's the thing that we need to remember here, is that we can't just switch these. We also need to switch the stuff in our augmented matrix, right? So now we're looking at this, right? And that's really important because if we were to not switch these and go through RREF, we would be finding the inverse to this matrix, not this matrix, okay? But we can keep going from here, right? Because we did remember to switch the part of our augmented stuff. And we want to, one by one, clear out the entries of this matrix, okay? We always start with the second row, so why don't we start with the third row, right? We can take row 3, we can subtract row 1, and redefine row 3 that way, okay? And we can copy this guy, and we can paste him in right there. We're changing row 3, so that guy's got to get erased. So what's going to happen here, right? We're going to have, it looks like, 1 minus 1 for 0. We're going to have, it looks like 1 minus 2 for -1. We're going to have 4 minus 7 for -3. We're going to have, looks like 0 minus 0 for 0. 0 minus 1 for -1. And we're going to have 1 minus 0 for 1. Okay? Next up, we want to clear this entry here. So we can take row 2. We can subtract 2 times row 1. Use that to redefine row 2. We copy our matrix over. We're changing row 2, so we need to erase it, right? And what do we get? Well, we're going to get 2 minus 2 for 0, which is exactly what we wanted, right? We're going to get, looks like we're going to get minus 3 minus 4 for -7. We're going to get minus 7 minus 14 for -21, okay? We're going to get 1 minus 0 for 1. We're going to get 0 minus -2, or sorry, 0 minus 2 for -2. And we have 0 and 0 there, okay? And you may already start to see a little bit of a problem here, but let's just sort of, keep moving and seeing what we get. Well, we're going to want to turn this guy into a 1, this negative 7 isn't really going to help us clear a 2 or a negative 1, right? So let's take row 2 and just multiply him by negative 1/7, right? So what do we get when that happens? Okay, well, all of these non-zero entries are going to change. They're going to get divided by negative 7. So we're going to get a 1, looks like we're going to get a 3, we're going to get a 1/7, and a -2/7. And this is already starting to look like a problem, okay? What happens when we try to clear this negative 1? Well, we're going to do that by taking row 3, adding row 2, and redefining row 3. And what does that give us? When we paste that in, we're changing row 3. And what do we get? Well, we get a 0 and a 0, still gives us 0. Looks like we get negative 1 plus 1 for 0. We get negative 3 plus 3 for 0. We do also need to remember to negate our elements there, because we did negative 1/7 here. But for here in what was our identity matrix, right, we're going to do 0 minus 1/7 to get minus 1/7, right? We're going to do negative 1 plus 2 over 7 for minus 5 over 7, and we're going to do 1 plus 0 for 1. And so if you look at what we're doing here, okay, what we would want to do next, right, we would want to clear this 2, but then we would want to clear this 3 and this 7. And we don't have a way to do that, right? There's a row of zeros here. And so what that tells us is that there is no inverse, right? Whenever you get a row of zeros, when you're going through the process of finding an inverse like that, like this, that automatically tells you that we don't have an inverse, okay? It's not very good spelling, so I'll write that again. And a matrix that does not have an inverse is called singular. So let's turn our attention to a different kind of example, okay? And that is using one of the things that we kind of noticed last lecture, and that's that our good friend system of equations and matrices are this, and matrix multiplication are, two sides of the same coin, okay? Minus 3y minus 6z, 3 plus 6y plus 15z, right? And we'll say that that's equal to 7, 5, and 0, okay? And so if we want to solve this system, okay, remember we can break this up into a piece of matrix multiplication, right? And when we break up these coefficients into a matrix, we're going to have 1, negative 2, negative 4, 2, negative 3, negative 6, and 3, 6, and 15, right? That's going to be multiplied by x, y, z. And it's going to equal 7, 5, 0. And this guy is called our coefficient matrix. Okay. Right now we'll just call him A. But if you hear me or anyone reference a coefficient matrix, that's this guy, okay? Let's say we'll call this guy X, and we'll call this guy B, okay? And if we wanted to solve this like an old-fashioned algebra question, this is how we do it, right? We have the following equation. We have that A times x equals b, right? Now, normally, we would divide by a, but division isn't defined here, right? So what we can do is we can multiply on the left by A inverse, okay? And remember, we're going to get these parentheses. But one of the nice things about matrix multiplication is that even though it's not commutative, we can't multiply A on either side. It has to be multiplied here on the left. We can reassociate. We can change this into A inverse A times x equals A inverse B. But if you remember, A inverse times A inverse is our identity, right? In this case, this is the cubic, or this is the 3 by 3 identity because we're talking about this system. But none of this work has required a specific dimension. So this does indeed work in n dimensions, or in an n by n matrix. Okay, so we get in times x is A inverse B, or since multiplying by our identity doesn't change anything, x is A inverse B, right? So if we know the inverse to this matrix, we can solve this equation rather quickly, right? So let's go ahead and do that. Because if you notice, this matrix was one that we already found the inverse for. So what that means is we can say that my xyz, right, well, it's equal to A inverse, which we said was -3, 2, 0, -4, 1, -2/3, and then 1, 0, 1/3. Okay? And then that needs to be multiplied by our b, which is 7, 5, 0. Okay? And what happens when we carry this out? Well, we're going to get a column, right? A 3 by 1 matrix here. Looks like this is going to come out to -3 times 7, plus 2 times 5, plus 0 times 0. Our second column, or our second row, rather, we're going to have -4 times 7. Looks like plus 1 times 5. And then in our last one, we're just going to have 1 times 7, because this 0 cancels with that, and this cancels with that 0. Okay. So when we perform this arithmetic, we're going to get the following solution. Looks like to me we're going to get -11, -23, and 7. Okay. And so if you happen to know your inverse matrix, we don't need to go through, doing Gaussian elimination on our coefficient matrix if we have another way to find the inverse, right? If you were, say, for example, solving a 2 by 2 system, right? We were doing something like this, it'd be 2x minus 5y, 3x minus 6y. We'll say that's equal to 15 and 36, right? When we write this as a matrix equation, we have 2, -5, 3, -6, times xy equals 15, 36, right? Once again, this is our coefficient matrix A, this is our unknown matrix X, this is our B, and we saw before that X is A inverse times B, right? Well, how do you find the inverse of a 2 by 2 matrix? Well, you do 1 over 2 times -6 is -12, and then we're going to subtract 3 times -5 is -15. Then you multiply that into, we switch our elements along the main diagonal, and we negate the elements on the off diagonal, right? And that's going to equal 1/3 times -6, 5, -3, 2. And here's a thing that's really nice, right? Our matrix multiplication is associative, even with our scalars, right? So if we have that x equals A inverse B, it's 1/3 -6, 5, -3, 2, times our b of 1536, what I can do is I can do this multiplication and then multiply by 1/3. Then I don't have to worry about my fractions until the end, because these two would give me some pretty nasty fractions, right? So what happens when we carry that out? Well, we're going to have 15 times -6 plus 5 times 36, right? All this is multiplied by 1/3. I guess I'll give us some more room. We have 1/3, okay, times that. And then we're going to have, it looks like, 15 times -3 plus 2 times 36, right? And when you run through this math, you're going to get 1/3 times 90 and 27. But now I can multiply in my 1/3, and I can solve my system thusly with x is 30 and 9, right? When we have these 2 by 2 systems, rather than using a substitution or an elimination method, we can convert straight into matrices, get my inverse, and do some matrix multiplication instead. Okay, so that's going to wrap up this lecture on these inverses. Stick around later in the week and we will do our last lecture on the determinant. So I'll see you then.